What did you call this lesson?
And other things.
Explosions and other problems. So we'll look at explosions at the end, but first of all, let's look at some more collisions at angles. In fact, I like example one, I like example one, I like example one. The level of difficulty you can expect to see is fairly close to this. And you'll see what I mean in a second. So I read along, a 10-kilogram curling stone is sliding along the ice, hits a stationary bucket of sand. After the collision, the curling stone's velocity is 3 meters per second east. As soon as I see that east, I start worrying that there's going to be angles. And then I see that 43 degrees south of you. Okay, so I'm going to draw compass rose to start out. Darian, what's this question want me to find?
Initial velocity.
Is there a collision?
Yeah.
You know what this is a job for?
Conservation.
Conservation of momentum. So I'm going to start out by saying, okay, there's a collision. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Check. That hasn't changed. Before the collision, what's moving? Do you want me to say mass 1, mass 2, or do you want me to say the stone and the bucket? I don't care. I'll do either. Okay. The stone, I'll use S for stone, B for bucket. Before the collision, what's moving? The stone, the bucket, or both? Momentum, stone, initial. PSI, that's imperial. We use metric. Wham, they collide. After the collision, wham, they collide. After the collision, what's moving? Mass 1, mass 2, the stone, the bucket, or both? I think both. Elastic or inelastic, stuck together or bounce off each other? Elastic. So it's going to be momentum of the stone final, momentum of the bucket final. And this is where I pause and double check. Cole, is everything in a nice straight line? Angles. So I dulp. What's the direction of the stone before the collision? It's a trick question. Don't know. Okay. After the collision, what's the direction of the stone? East. How big? Mass times velocity. Again, don't just put the 3 on there. You know what? It's 10 times 3. I can do that in my head. It's 30. Plus. Cole, can you read me the direction of the bucket? The what of what? The how many degrees what of what?
43 degrees
south of what? South of what? I'm going to draw east first. What of east? I'm going to go south. How many degrees? Which is nearly 45, so I'll kind of eyeball it. Now, how big is this line? Mass times velocity. It's going to be 18 times 2.3. Right? Is that okay, Riley?
Yep.
It's going to be 41.4. Now, the reason I said I like this question, you'll notice in this question here, the two vectors that I'm adding, I know them both. This one does not involve vector subtraction. I would have no problem giving you a nasty vector subtraction as a multiple choice, but as a written, you can almost certainly expect it's either going to be adding together tip to tail, or it's going to be one that you can eyeball. Even though you're technically subtracting, you can just kind of draw it and figure it out. I'll show you that next. Anyways, how would I add those two vectors together? Draw them. I'm going to do it. I got a nice big triangle area up here, so I'm going to go yoink 30. Then I'll draw the 41.4 about 1.5 times as long. can you see what the resultant is? The direction of the stone when it was coming in must have been that there. In fact, Anthony, if this was a multiple choice question, I'd cross out any answers that didn't have the words south and south and east in them. Anything that had a north or a west, I'm crossing that out. I don't even need to think. In fact, you might even be done. You might find, oh, holy smokes, there's only one answer that has south and east. It's got to be that. I'd quit then and just circle it. Now I need an angle. Now, looking at this, it looks like the angle that they gave me, is that one there, 43 degrees. Which is unfortunate because that angle's not inside the triangle. Or is it? I'm glad people are making a mistake. I see a few people doing the Zorro thing. Zorro does not work, and I'll show you why. Zorro only works when the top and the bottom parts of the Z are parallel. You can't have a horizontal and a slanty. They can both be identically slanty and they'll work, or they both be horizontal and they work, or they both be vertical and they work. This is not a Zorro. This is not an alternate interior. The Z doesn't work. So what does work? That. What kind of an angle is that? 180. So if this is 43, gotta be 137. I think, double check my math, but I'm pretty sure that's right. Okay. And now, hopefully, we're starting to get into repetitive territory in that, I would say, SOHCAHTOA. By the way, the only time it'll be SOHCAHTOA, Miller, for a two-dimensional collision like this is if all the directions are north, south, east, west, if there's no thetas. So as soon as that 43 appeared in the question, see the 43 degrees, I knew it was going to be non-right angle. Okay? But if they had said that the bucket went east and the stone went east and the bucket went due south, those I can add tip to tail and use SOHCAHTOA Pythagoras. Okay. Anyways, it's cosine law. How can I tell? Well, you may notice that almost always it's the cosine law when the angle's across from what we're trying to find. You can also tell because it's side angle side. You can also tell because this triangle does not have a pair that we know. Cosine law. What's the cosine law going to be? It's going to say the stone squared equals 30 squared plus 41.4 squared minus 230, 41.4 cos 137. I left you guys the whole half page, right, to get this done? Lots of room? Okay, good. On this line, at this stage, I like to go to my calculator and do this all in one fell swoop. Hopefully you've heard me do a calculator rant or two or 10. .30 squared, 41 point minus 2 times 30 times 41.4 cos 137. Square root. Do you get 66.563 blah, 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 blah? Someone double check me. Yeah. So Miller, I get the initial momentum was 66.563 blah, blah, blah. But that's not what they wanted me to find. What did they want me to find? How can I find a velocity if I know a momentum? By the way, I should be careful. Really, what I should be saying is, how can I find a speed if I know a momentum? Divide by the mass, and then do some trig to find the velocity by adding the direction. So what was the mass?
10 kilograms.
I think I'm going to divide by 10 in my head. I'll write it here. It's going to be 66.563 over 10, which is going to be 6.66 if I go to 3 sig figs. 6.656, but the 5 would become a 6 because of the 6 next to it. 6.66 meters per second at I need direction. Oh, this one's pretty good. If I go look where my vector is coming from, right there, that angle is one that I can use because part of it is horizontal. It is a what of what fact. That angle there is a what of what? That's the south of east. All I need to do is find its magnitude. How? Sine law. Sine law. Because now I have a pair. It's going to be the sine of the mystery angle divided by what's across from it equals the sine of 137 divided by what's across from it, which I used to not know, but now I know is 66.563. By the way, common mistakes I see, kids put the velocity there instead of the momentum. Don't do that. Its momentum is conserved. How would I get the sine theta by itself? Times by? So I'm going to go 41.4 sine 137 divided by, haha, answer button. And the angle is 0.42, what? Oh, no, that's not the angle. It's the sine of the angle. 25.1 degrees. 25.1 degrees. What did we say it was? What of what? That, to me, is a totally fair game B-level question for a test. Not an A level, because we didn't have to do subtraction, or the angle wasn't yucky to find, we didn't have to add extra lines or anything like that. So that totally fair game. What else could I ask with a question like this, Dro? Huh. Next page. Here's a collision again. This time they gave me a lovely diagram. That's nice. It says, find the final velocity, magnitude, and direction of the 10 kilogram mass. You know what? That's got to be fairly similar, I think, to what I just did. Oh, B, little twist. Find the amount of kinetic energy lost and transfer it into heat. Okay. Oh. Let's keep going. Sarah! Is there a collision? Angles? You know what? I can tell right from the picture. I've turned the page. I think you guys are still on the same page, but I'm going to put a little compass rose here somewhere. Hey, Sarah, if there's a collision, what's this a job for? So the sum of all the momentum before equals the sum of all the momentum after. Looking at this wonderfully artistic picture, let's call the 2 kilogram mass mass 1 because it's the first one that appears. The 10 kilogram mass will be mass 2. Before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. Wham, they collide. After the collision, both. Stuck together, separate. Separate. Angles, yup, dope. Draw a little picture. Sarah, looking at the picture, or reading the question, what's the initial direction of mass 1? East, so I'm going to draw this. Yoink. And I can even tell you how big. It's mass times velocity. It's 2 times 8. In your head, Sarah, is what? 16. 16. They collide. Wham. Remember, mass 1 is the 2 kilogram. What's the direction, Sarah, of mass 1 after the collision? Yep, now they gave me a picture, so I could even have just gone, well, it's going to look like that. And I can tell you how big it is. It's going to be mass times velocity. It's going to be 2 times 6.7, which I think is 13.4. Someone double check. 2 times 6.7. Is it 13.4? And Sarah, it also looks like, according to the picture, that angle right there is 10 degrees. There's my south of east. Plus. What direction is the velocity of object 2, or the momentum of object 2? Well, Sarah, the written part doesn't say, but looking at my picture, I think I can safely, looking at the picture, say, you know what? That way. Right? This to me is also fair game, although this is technically a vector subtraction, because technically I could also subtract to get this by itself. I think the picture gives me enough info that I can actually still do it by adding. I think what I can do, let's call this momentum 2 final. I think I can draw a triangle where I add these two together tip to tail, where it's going to look like this. Here's my vector triangle. 13.4. Now, why can I do this without doing the subtraction part? Because, Carl, the answer that they gave me. When I add the right-hand two vectors together, it has to equal 16 in what direction? Loudly, with authority. Which means drawing a vector like that, too big. Because now if I draw the resultant, that ain't east. And it means drawing the vector like that, too short. Because if I draw the resultant, that ain't east. Now, Carl, there is some leeway because you might want to draw your vector like this, and someone else might draw it like that. Someone else might draw it like that. You know what? I'm going to kind of split. Usually what I kind of do is gut instinct split the difference. I'm going to say, you know what? There's momentum 2 final. And that's why I can add a resultant of 16. The other thing that makes this one a little nicer than some of the ones we did last day or during lesson 6.5 is theta. Sarah, can you see the 10 degrees actually fits right? It's got to go right in there, right? Because it looks like the 13.4 below a horizontal line is 10 degrees, and I have a 13.4 below a horizontal line in my triangle. If I've done my job right, Alon, now we're getting bored and repetitive. This is now, after this, plug and chug. And yes, it's pretty complicated, plug and chug. But look, Alon, SOHCAHTOA, is there a right angle in my triangle? You know what? It's going to be cosine law. And it almost always will. Not always. I'm going to show you one where it's not later on today. But often it's going to be cosine law. Then I'm going to divide by the mass to get the speed. And then I'm going to find the sine law to get the theta. Well, let's go. So it's going to be momentum 2 final squared equals 13.4 squared plus 16 squared minus 2. 13.4, 16 cos 10 degrees. Now, by the way, looking at my picture, my scale is going to be kind of garbagey because my 10-degree angle, Trevor, is closer to 45. Look how I've drawn it. So the scale is going to be a little yucky, but I wanted to have a nice big triangle that I could write in, and I worried that if I actually went 10 degrees, which is probably only about like this, I'd end up with a triangle that would be awkward to work with. Okay? And I end up with momentum 2 final equaling Oh, no. square root 3.6434. Blah, blah, blah. And Anthony, do you see what I mean by this is terrible scale? Because this is 13. This line looks like it's the same length, but actually it's 3.5, 3.6, whatever. Now what? That's the momentum. Not what this question wanted me to find. What did this question want me to find? How can I find velocity if I know momentum? Well, I can't. What I can find is the speed. How? Divide by the... was the mass 10 again? Is it the 10 kilogram mass that's moving? Look at the picture. Look at the picture. Is it the 10 kilogram mass? By the way, don't make that mistake. Look at the picture. Look at what we're finding. Look what I don't know. I think it's the 10 kilogram mass. That's the mystery. So point being, I can divide by 10 in my head. It's going to be 0.364, right? Meters per second at... I got room kind of up here and to the right to do the sine law. Sine of theta divided by what goes under here? What's across from theta? What is across from the theta? I don't have a theta yet. That's a problem, Mr. Dueck. Why? Look up. Why would this be a bad theta to pick? Why can't I use that? Yeah, it's a nothing of nothing. It's a slanty of slanty, but it ain't no north of east or what. Okay, so the only other option I have is this is where I have to add a line. I'm going to add a horizontal line right there and call that theta. By the way, that theta there is going to be what of what? North of south, east of west, what of what? I've heard three different. What is that? Where I've drawn it. North of, it's the north of east. So I'm going to leave a space, and I'm going to go north of east. Now, the only problem with that theta is it's not in my triangle. Or is it? Now there's a Z, a proper Z. Now I can say, let's try that again with the highlighter, Mr. Dueck. Because the top and the bottom are parallel. Which means, now Anthony, although the angle that I'm finding, by the way, is south of west, that's not what I want with my vector. With my vector, which, so look at the way the arrow is pointing, it's definitely north of east. But now I can use the sine law. There's my theta. What's across from the theta? 13.4, and that equals the sine of 10 over what's across from the 10, which was 3.6434. $13.4 times. Why put a theta there, Mr. Dueck? It's a 10. Let's try that again. Sine 10 divided by 3 point... Oh, wait a minute. Divided by answer button. Still have that stored on my... Because it divided by 10. I didn't even write anything. Oh, that's the sine of theta. .7 degrees. Don't be turning the page, Darian, because that's only part A. You should. Do you have room beneath the typing though? Because that's all that's all you're gonna need. What does B want me to find? Okay, that's quoting the question. In terms of physics, what's B asking me to find? You know what? It's asking me to find that. Because this is a top view, so there's no change in potential. It's all staying flat the whole time. Any energy that has been lost, heat, kinetic energy change. Where change in anything is what? Now, don't write yet. I'm going to do this a little bit differently for a reason. You'll see why in a second. I'm going to say this is, and I'm actually going to write out the word final, takeaway, initial. And the reason is, before the collision, how many objects are moving? 1. After the collision, how many objects are moving? 2. So I want to stay away from using a symbol where I might only think one thing is moving. I'll write final minus initial, and I'm actually going to say, okay, so here's the final minus, and then, now initial, that I can do. One object moving, what's kinetic energy been, holy smokes, since last year, since Physics 11? What's the equation for kinetic energy? A half, 0.5. What is the mass of the object that's moving at the beginning? 2. And what's v squared at the beginning? 8? Even? Okay, there's my initial kinetic energy. After, how many objects are moving? 2. Now, are there angles? I don't care. Why don't I care? Oh. Okay, so I don't know, whatever, and by the way, this also is why I said in the last unit, race cars are designed to literally explode almost on contact if there's an accident. Every piece that goes away, even if it's not transferring momentum with it, but it sure is taking some energy with it. That's a plus. Let's do the 2 kilogram mass is going to be a half times 2 times, how fast was the 2 kilogram mass moving after the collision? Look at the picture, or did we calculate it? I can't remember. Did the picture tell us? 6.7 squared? And you're adding, I thought it was final minus initial. Yeah, it's all the final. So add all the final together, minus the initial. A half, 10. Oh, and we just calculated how fast the 10 was moving. 0.364 squared. There is my final, all of it, takeaway initial. I think I'm expecting a negative answer here, because I think I am losing energy. Sorry. I think I am losing kinetic energy. You're never losing energy. I think some of it did go into heat and deforming the objects and making noise and all that. So here we go. A half m v final squared plus a half m. I can even go a bit more specific because I have that up there. Squared minus a half m8 squared. And looks like I lost negative 18.4 joules of kinetic energy. So, is momentum conserved always in a collision? Is total energy conserved? Always in a collision. Is kinetic energy conserved? Nope. Unless it's a perfectly elastic collision. So perfectly elastic means they bounce off of each other and there was no sound or heat or deforming. Is there such a thing? Actually, at the atomic and subatomic level, yeah. And in theory, curling rocks are close because they have identical masses and they're very, very hard. Oh, wait a minute. I've watched curling. I do hear the impact, though. So you're losing some kinetic energy there. By the way, curling, great example of momentum with angled collisions, right? The only reason I don't do a bunch of curling questions is in real life, all the rocks have identical masses, which means if you do anything algebraically, suddenly your masses all cancel because all the rocks just happen to be identical. But I don't want you to think, unlike energy, masses cancel. Well, no, it's by a fluke, all the masses were identical, so I kind of avoid them. There is going to be a bonus video game up this weekend. I'll email out some information for this unit, and it's going to involve collisions at angles. Turn the page. Oh, Ben, going back to the last question. I sort of like it. I sort of like it. I sort of like it. Here,
It might be on the test.
I would have, to me, cosine law and then find some energy is overkill. However, if I gave you a nice angled collision where everything was at right angles, and you could use SOHCAHTOA and sine and cosine and tangent, then a nice part B would be, hey, find how much kinetic energy was lost. Okay? But I don't think, I know in the review and I think on the take-home quiz, I give you find the change in energy for a big yucky angled cosine law collision, and that's great. On the test, I'd consider that overkill. On the written, I would have no problem as a nasty multiple choice giving you the question we just did, but not asking you A, just simply saying, tell me the change in kinetic energy, and you'd have to say, oh, I better find all the speeds and velocities. Although, you wouldn't have to find theta, because once you found the speed of the second object after the collision, you could go straight to energy because it's a scalar. Example 3. I like example 3, I like example 3, I like example 3. Something like this. So you have one mass incoming, nice and straight, glancing off another mass. Okay? I'm going to make a suggestion. I'm going to pause the video and I'm going to suggest try solving this on your own. I'll keep my screen up, look up if you get stuck. But if you want a good, hey, I'm in pretty good shape, try this one. You can work quietly with your partner, ask them questions, your neighbor as well, if you have a neighbor. If you have a reliable neighbor.
Rest in peace, Kai. We never let him rest in peace.
Oh, I have him in another block, and believe me, it goes on.
I know. He's
Yeah.
telling me. It's him and Giancarlo looking at me.
Good, shut up and solve this. Got a phone, Kai?
Yes, I do. Can I use that?
I'll put up with it as long as it doesn't make any noise.
And I have a scientific calculator.
Oh, bravo. I've turned the page, so I'm going to throw a I can already tell you I'm going to do compass rose here. Although I guess technically there's nothing in this question that says I can assume that north is up, but I'll assume that north is up. I'll let the video recording run so people can see my work, and I'll give a bit of quiet narration so that people watching on YouTube don't think the sound is turned off or something silly like that. Before the collision, it's going to be... After the collision, it's going to be... Hey, Mr. Dueck, what if they stuck together and moved off at an angle? Thank you. And what if they stuck together and moved off at an angle after the collision? Oh, it would be just mass of both, but I think I could still solve this. It'd be a little weird. Or, you know what? You could have them both coming in at an angle, sticking together and moving off in a nice straight line. That'd be cool. In fact, that's actually probably a tackling or a hockey body check question. Dolp. Mass times velocity, 102.85. I made these numbers up just before Christmas when I created this lesson, and I didn't work them out ahead of time. This triangle is going to be terrible scale because I noticed my incoming momentum is 102.85, and I notice my final momentum of the second object is like 15.73, which is really short. I really should draw a short, and it's going to be yucky triangle, so... can draw this tip to tail. Really, Riley, my triangle should look like this. Right? That's about the length of 15 compared to 102, but that's just going to be too awkward to do work in. So it means I suspect this angle here is really small, probably less than 15 degrees, and it looks like eyeballing it like it's like 45. It ain't. So I'm not going to freak out. This is nice, though. It gave me an angle in the triangle. Oh, not squared here, Mr. Dueck. Did I type that in right? Okay. Let's go back again. This seems wonky to me. Squared. 102.8 squared. Minus 15.7. 102.85 cos 38. Yeah, okay. 90.9715. Okay. What was the mass of object 2? 4.2. 21.7. Okay, let's cleverly get that 90.9715 back. There it is. So it's going to be that times that divided by that. Square root. Yeah, this is going to be a really small angle. Like, no, that's not what I wanted. Wrong button. Let's try that again. Shift sign. Yeah. I may be wrong. I did this in a rush, but if anybody else gets there, then we'll either both be wrong together or maybe we're right. You got that? Yeah? Okay. There seems to be a consensus. If you've got that on at least one of the written questions, maybe two, as long as you don't make mistakes, you're in great shape. Thumbs up, Riley? Yeah. By the way, last class, one of the kids was, I can't get the right angle. I'm getting the wrong angle every time, Mr. Dueck. And the mistake he was doing was, instead of putting the 90.97, the momentum, he's putting the 21.7, the velocity. That happens fairly often because they're so, got the velocity, and it's fresh on your calculator, staring you in the face. Put the momentum down there. It's momentum that's conserved and is on the triangle, not velocity. Perfect. Pardon me?
Don't need the marshmallow.
Yeah, that too. So if we got the hang of that, let's blow some stuff up. Turn the page. I did promise you explosions. Okay. Example 4. Example 4. Read along with me. A metal disc explodes, boom, into 3 pieces, which fly off in the same geometric plane. We're going to keep them flying off flat. In real life, bombs blow up upwards as well as outwards. But this is the start of, for example, forensic investigations of bombs. Although we're going to have it blow up into 3 pieces. In real life, it blows up into thousands, and you use a computer, but you can actually crunch everything, starting with the initial momentum, and figure out and predict where pieces might have landed if you know the original mass of the bomb, and you say, okay, we've got these pieces. Oh, there's a piece over that way, 2.5 kilometers. Go look for it. You can do this. Flies off, explodes into 3 pieces. The first piece has a mass of 3.4 kilograms. It flies off north. The second piece has a mass of 4 kilograms. It flies east. I just saw 2 different directions. What's the speed and direction, velocity, of the third piece, which has a mass of 2.4 kilograms? Okay. This is an explosion. You know what that's a job for? And this is why a few days ago I said we use conservation of momentum for jeunes, for collisions and explosions. Jeff, we're going to start out the same way. We're going to start out by saying, you know what? The sum. The sum. Before the explosion, what's moving? Mass 1, mass 2, mass 3? It's a trick question. Boom! They explode. After the explosion, what's moving? Mass 1, mass 2, mass 3, all or none? Stuck together or separate? Directions in this question? Yep. Draw a picture. So I get this. 0 equals, what's the direction of mass 1? North? Yoink. How big? Mass times velocity, 3.4 times 11, 37.4? Darian. Miller smiling. Plus, what's the direction of mass 2? Yoink. Oh, timesing by 4. I should be able to do that. That's times by 2 times by 2. 13.5 times 2, 27 times 2. Is it 54? Double check me. 13.5 times 4. 54? So when I draw it, I'll make sure I draw it longer than the 37.4. Plus, what's the direction of mass 3? Question mark. Okay. Well, I have 3 vectors on the right-hand side. How would I add them tip to tail? So let's draw. Let's dope. I would go like this. There's the 37.4, and apparently tip to tail I would add 54. Now, the third vector is a mystery, except I know what the answer when I add these 3 together is supposed to be. What's the answer supposed to be when I add these together? What does 0 look like as a vector? What does 0 look like as a vector triangle? If this was a displacement, what would a vector triangle of 0 look like? Back to where you came from. If this is 0 moment, oh, you missed that. Behind you, Miller went like this. He went like that. There you go. So Because the question, most kids can get this part, but they're asking, hey, do I draw it pointing this way or do I draw it pointing this way? Because the momentum is 0, as a picture, it must look like that. That's 0. That's the momentum of object 3. Back to where you came from. Oh, and you know what else is nice about this puppy here? Oh, Pythagoras. It's going to be momentum 3 squared equals 37.4 squared plus 54 squared. By the way, don't write this next bit down. Cosine law works. Because it is a 90-degree angle. And the reason it works on your calculator, what is the cosine of 90? Try it. What's the cosine of 90? Try it. What's the cosine of 90? It's not 1. What is it? Oh, which really just says, you know what? This all would cancel. It turns out Pythagoras is a special subcase of the cosine law. The cosine law is universal Pythagoras. It's going to be... So the momentum of that third mystery piece is 37.4 squared plus 54 squared square root. 65.6868. It's not what they asked me to find. What did this question want me to find? How can I find the speed if I know the momentum? What was the mass? I've scrolled down. Was it 2.4? So divide by 2.4. So it's going to be 65.6868 divided by 2.4. I get a speed of 27.4. 20 boop. Let's try that again. Meters per second. They did say direction. Now here's the nice thing, and this is why I said it's almost always the cosine law and the sine law, but not always. I think the direction would be this angle right here, which I think I can go and bring back our old friend tan, what the basketball players were doing in Hawaii, except for Jordan and Tyler, but that's okay. Tan theta equals opposite over adjacent. I like this question, I like this question, I like this question. I think so, yeah. Now, I think on your take-home quiz, I give you an explosion that's cosine law and sine law, but I think I decided on the test I'll give you an explosion that's nice right angles, where everything magically blew up north, south, east, west, and only one of them is slanty. How big is the angle? It's going to be shift tan 37.4 opposite over adjacent. 34.7 degrees. What of what? South of west. Right? See? We're heading back and left, down and left, right? South and west. Explosions. You know what? Another good example of this. How many of you have ever been tried to balance out in the water on like an inner tube or a little rubber boat or something like that? And if you try and dive off, what happens when you try and do that? What does the boat or the inner tube do? Moves in the other direction. Why? Because beforehand your momentum is 0. If you want a positive forward momentum, for the momentum to still be 0, the inner tube has to move backward. Hey, what has more mass, you or the inner tube? So the inner tube has to move back faster than you're going forward, which is why it doesn't work very well. Or the one I used to see all the time, I used to work at a summer camp and I used to teach canoeing, and I would see people, when they came back from canoeing, stand up. they would put 1 foot on the dock. Now, as soon as they try putting 1 foot on the dock, what they're really doing is they're trying to give themselves sideways momentum, and their initial momentum was 0. So if they're giving themselves momentum to the left, which way must the canoe move? To the right. Splits, splash, and lots of fun. And then they learned there's a better way to, you stand up, you pivot, momentum is still 0, you sit down, then you lift your legs out, right? Or you hold on with another, I mean, the other way is you just hold on and you exert an extra force, but now you have an external force. This was cool. We did this last class. This is a roller coaster going down a hill, hitting another coaster, sticking, and how high do they go? This is cool. It's a nasty scholarship, but I'm going to skip it. What your homework is, so I'm going to give you the ultimate review.